Welcome back, guys. This time around we're going to take a look at skeletal muscle metabolism. Now, if you recall, metabolism has got two sets of reactions, catabolic and anabolic. In this case, we're specifically going to be looking at the catabolic reactions. We're going to be looking at where does all the ATP that is needed during a muscle contraction get generated at within a muscle cell. Now, to thoroughly understand that, we got to understand where is all the ATP being used at. It's being used basically as two different ways. One is a pump. Now, a pump means that it's pushing, in this case, ions, sodium, potassium, and calcium, against the concentration gradient. It's moving them uphill, upriver, typically during the relaxation phase of the contraction. The other way in which ATP is being used, it's being used during the contraction itself. If you recall, we have that cross-bridge attachment, pivot, detachment, myosin head group cocking. Now remember what triggers the detachment. What triggers the detachment is going to be the ATP. So in summary, we're going to have ATP in the muscle contractions for two reasons. As a pump mechanism to take us back to resting state, and secondly, to recock the head group so that we can have another cycle during the muscle contractions. Now, where does all this ATP come from? All this ATP, it would be really nice to think, would be stored within the muscle cell to allow us to have maximum muscle contractions without ever having to worry about any negative byproducts. Truth be told, there's enough ATP in a typical muscle cell to do 4 to 6 seconds worth of contractions. The rest of it's got to be produced during the contraction process. And it's going to be produced in one of three ways. Either direct phosphorylation of ADP by creatine phosphate, anaerobic respiration, or aerobic respiration. Let's look at these each individually. Direct phosphorylation would be an instance in which we take a high energy molecule called creatine phosphate and we transfer the phosphate group from creatine phosphate to an ADP molecule that is found in the cell. Why can this happen? The reason why this can happen is creatine phosphate has a much higher energy bond on that phosphate than what we find associated with the ADP. What's the end product of direct phosphorylation? For every creatine phosphate molecule we have, we can regenerate one ATP. And the end product of the creatine phosphate when it transfers that phosphate group is creatine. Now, creatine is going to be found only in muscle cells. One of those muscle cells could easily be your heart. When you become a nurse or a health professional, you're going to be looking for indicators for a massive heart attack, because with a massive heart attack, an individual actually physically tears muscle cells, and the contents of those muscle cells are released and usually accumulate either in blood or in urine. One of the telltale triggers of that is creatine, because you're looking for the levels of creatine to rise. If the heart attack was a massive heart attack, it resulted in tearing. Because we also know that we have a second type of heart attack, a muscle cramp. No muscle cells are torn, so no creatine would accumulate in the blood or in the plasma. Now, we have enough creatine phosphate found in the muscle cell to typically result anywhere from 15 to 20 seconds of additional ATP. So cumulatively, with the ATP that's stored in the muscle cell, plus the ability to direct phosphorylate using creatine kinase, we can generate about 20 seconds worth of ATP needs. That typically is 1, not enough, and 2, not quick enough, because creatine kinase is not a real fast reaction. So we also have to employ other pathways to generate energy. One of those pathways is known as anaerobic respiration. The other pathway is known as aerobic respiration. Remember what the difference between the two. Aerobic means in the presence of oxygen. Anaerobic means in the absence of oxygen. But they both have the first pathway in common, that is glycolysis. Because with anaerobic respiration, glycolysis is going to be the breakdown of a glucose molecule. Notice that glucose molecule is broken down in the cytoplasm. End products of anaerobic respiration would be the production of 2 ATPs per glucose molecule and an pyruvic acid molecule, or pyruvate. Now, pyruvate's not water soluble, and so we convert pyruvate in the absence of oxygen to lactic acid. So it can be released into the blood at some point in time. And when it's released in blood, it will travel to the liver and it'll be converted back to glucose molecules. Now, is anaerobic a good process? It is in some regards, and in others it's not. It has its pros and cons. For each glucose molecule that is broken down anaerobically, we do generate 2 ATPs. Now, if you compare that to aerobic respiration, we produce 32 ATPs per glucose in aerobic. So you're looking at only about 5% of the amount of energy that can be produced from that glucose molecule aerobically is being produced anaerobically. Bottom line is, if I do anaerobic respiration, I can generate, by breaking down glucose, I can generate about 40 ATPs in the same amount of time it takes me to take one glucose molecule all the way through aerobic respiration to produce 32. So on the short end, I'm more efficient at producing energy in the form of ATP anaerobically. The backside of it is, though, when I produce that ATP, I also produce the lactic acid. And the lactic acid builds up inside of that muscle cell. And as it builds up inside that muscle cell, it can cause the pH to become more acidic, causing enzymes to break down. In reality, practicality, I have about 30 to 40 seconds worth of anaerobic respiration that I can do before a typical muscle cell will start to, the enzymatic activity start to break down. So that means I've got about a minute worth of energy production between the ATP that's stored in the muscle cell, direct phosphorylation, and anaerobic respiration. Many muscle contractions, though, occur over a much longer span than just a minute. In that case, we're going to have to take advantage of the third and most efficient pathway, and that's known as aerobic respiration. Means that I'm taking glucose and I'm breaking it down to pyruvate. But in the presence of oxygen, I can take that pyruvic acid and bring it into the mitochondria. And if you remember, inside the mitochondria, there's two sets of reactions known as the Krebs cycle and the electron transport chain. The end products of aerobic cellular respiration are going to be no negative byproducts like lactic acid, only 32 ATPs. We make water as well. So for each glucose aerobically broken down, no negative byproducts, and 32 ATPs generated. So over the long haul, I would want to do aerobic respiration. This is why you become aerobically fit. Aerobically fit means that one of the key things it means is you increase the amount of vascularization you have, so that you can increase the rate at which you can deliver oxygen to the muscle cells during maximum exertion. Notice also with aerobic cellular respiration, you can use other foodstuffs as energy sources. With aerobic cellular respiration, we can also include fats and amino acids, proteins that those amino acids come from. This can continue as long as I can get oxygen to the cell and as long as I have glucose or fat sources or proteins available. The only thing that would stop the exertion or the contraction then would be an imbalance of potassium. Because remember, with repolarization, potassium is pushed out of the cell and into the extracellular space. Over time, not all that potassium is capable of being reabsorbed because some of it will float away. And over time, enough of it will float away that I won't have enough potassium to do the repolarization when I have that muscle contraction. That's why when I played football, I'd have 2 a days. I'd have to increase the amount of potassium. Folks eat bananas as well for that reason, to increase the potassium level. Factors I'd like you to take into consideration as we talk through this process also is oxygen debt. What is oxygen debt? Well, back up just a moment. Remember, in a muscle cell, we have these specialized structures called myoglobin. And myoglobin are proteins that are capable of storing oxygen. And when I maximally exert myself, the first place I get my supply of oxygen will be from those myoglobin. I'll supplement the supply of oxygen then from the blood supply. Over time, I will deplete the amount of oxygen from the myoglobin, and I'll deplete the amount of oxygen that I'm able to get from the muscle or from the blood. And so over a short period of time or a long period of time, I will go into oxygen debt. Think of it as a loan. I'm taking money out of the bank, but I now need to put the money back in the bank. How do I do that? Well, whenever you're exerting yourself and running a short distance and you stop, what's the first thing you do? Well, if it's me, I take a deep breath. And I breathe deeply for a period of time. Why? That is your body's response to the fact that you're in oxygen debt. You need to replenish the amount of oxygen at the cell level, so it forces you to take deeper breaths, so you bring more oxygenated air in. More oxygenated air can be transported to the tissues level and stored. The other concept I'd want you to take into consideration is muscle fatigue. What is muscle fatigue? Well, if you're like me, it's not a psychological thing. In my case, I would say my muscles are fatigued before I even start exerting them. And muscle fatigue is a physiological event in which you result in the inability to contract. Now, most frequently during the contraction process, that goes back to what we learned in the microanatomy of the muscle, where we were looking at the cross-bridge attachment, pivot, and detachment. Remember, what caused the detachment was the binding of an ATP molecule at the ATP binding site on the myosin head group. Well, if there is not ATP present during the contraction for that binding to occur, then it's going to pivot, but it's going to stay there. That head group's going to stay there. And over time, we get what we call a contracture. We commonly call it a cramp from a deficiency of ATP due to overexertion. Now, these cramps can be influenced by the fact that we have lactic acid buildup, which causes enzymatic activities to wither down, or it can be due to the fact that we change the ionic balance within the muscle cell. But think about it. Did you ever wonder? And then the third thing I'd want you to think about there is, again, why do we have a muscle contraction when we're sitting out in the cold? Why does our teeth chatter? Why do we shiver? Now remember, when we do the aerobic cellular respiration, at rest, think about being at a football game and you start to shiver. And what the shivering is a result of is your body temperature dipping below normal, and your body's reaction to try to create more heat internally, because that aerobic cellular respiration that we keep going back to, it does result in production of 32 ATPs, but that's only about 50 to 55% efficient in converting the energy that's stored in glucose into actual molecules of ATP. The rest of that goes out as unusable or non-reusable energy known as heat. Now, we just discussed a number of challenges that could overcome us and cause us to have contractures and cramps. Most of those dealing with the ability to produce ATP aerobically or anaerobically. So how do we adapt to overcome these muscle physiology challenges? The way we adapt is that we create a variety of different types of muscle fibers. From this chart, you can see that we create slow oxidative fibers, we create fast oxidative fibers, and fast glycolyc fibers. Now, what would be the differences between these? Now, if I was looking at the slow, sometimes I call that red slow, and I would call it red slow fatigue resistant fibers. Now, why would I do that? Because take a look at what you would find in these slow oxidative fibers. You would find a lot of mitochondria, a lot of capillary. You'd find a small diameter to the fibers, which means that when the capillaries are there, the high number of capillaries are there, oxygen comes down to the capillaries, it can diffuse to the middle of that cell very easily. The mitochondria, a lot of mitochondria means that it can produce a lot of energy. It's going to be red when we look at it. It's going to be fatigue resistant, which means it's going to be slow to fatigue. Why? Because it's maximizing the ability to do aerobic cellular respiration. These are going to be very thin fibers, though. They aren't going to carry a lot of massive weight. These are the type of fibers that a long-distance runner would be trying to develop. And notice on the other end of the spectrum, we have these fibers known as the fast glycolytic fibers. Another name for those would be white, fast-twitch, fatigable fibers. Why would I call them white? I'd call them white because they have very few capillary beds. They have very few mitochondria. Now think about it. If they don't have mitochondria, then they're not going to use aerobic cellular respiration. But look at the diameter of them. They're quite large in diameter. Let's think about that. If they don't have mitochondria, they're going to be producing their energy anaerobically, which means lactic acid is going to be building up in it. So I would want these to be a larger diameter so that I have more space for that lactic acid to build up before the enzymatic activities start breaking down inside that cell. Where would I use muscles like this for? I would use these muscles if I was a weightlifter, if I was doing powerful motions like swinging a bat, if I was jumping like a basketball player does, sprinting like a short distance runner would do. Those would be the types of muscle fibers that I would be trying to develop. Now think about it. If you look at a football player, if you look at a weightlifter, are their muscles much larger? They are, because the individual muscle cells are these types of cells. They can't run long distances though, or they'll cramp up. If you ever watched a very strong man try to lift a lot of weights and do it repeatedly, you'll find they cramp fairly quickly. Then you've got the ones in the middle called fast oxidative fibers. These have got the best of both worlds. They're intermediate in diameter. They have quite a few mitochondria, not as many as the first one. They have quite a bit of capillary beds. It's not as many as the slow oxidative fibers do. They're going to be pink to red. They're going to use aerobic, but they're also capable of using anaerobic to some period of time because that intermediate diameter of their fibers. They'll have stores of glycogen there, and those stores of glycogen will allow them to break down the glycogen to produce glucose, and so that they'll have a lot of glucose present. Notice what kind of recruitment they use. Where would you see these types of fibers? Think about cross-training. It's going to be an excellent opportunity to see the development of these type of fibers, because if you're cross-training, you're actually producing those weight-bearing ones as well as those endurance ones. So if you're looking at somebody who walks, sprints a lot, they're building a combination of all three of these types of fibers. They're the healthiest of the group. That was a lot to digest. So now realize that I want you to go back. I want you to look at muscle anatomy again. Contractions, excitation, the excitation-contraction coupling events. I want you to look at skeletal muscle contractions gross level. Take a look at metabolism and consider the types of muscles that you have developed in your body and which types of muscles would you want to develop if you had the opportunity. See you next time. Have a good day.